Our next speaker is Professor Mike Zimmerman. Mike and I are old friends. I've known him for nearly 35 years now. I first met him when he was doing his PhD on injection molding of polymers. And he came with his PhD supervisor, Marty Lesser. And Marty Lesser was a great friend of my PhD supervisor, John Field. And of course, the two of them being friends, they asked me if I could help Mike with doing some experiments. Are you okay there, Mike? You good? And Mike was doing some modelling in those days of injection moulding of polymers into moulds. It was all quite new technology, and they wanted someone to help with some experiments. And initially I helped Mike with the experiments, but he got better in the end, and he was doing the experiments in the lab, and he kicked me out of the lab and took over. Anyway, he got his PhD, and then he went to work for Bell Labs in the US and rose to a very distinguished scientist rank, which is like the top 1% of Bell Labs scientists. He was there for 15 years, and then he left Bell Labs and set up a company which was called QLP, Quantum Leap Packaging. And I won't go into all the details because I'm at the next tour, but along the way he's met some very interesting people, Bill Joy of Sun Microsystems, and even Bill Gates. So I'm going to hand over to you, Mike. Are you wired for sound?
Can you hear me?
I think so.
Hello?
All good. Sam says all good.
Okay.
I've got to take a picture of you. Hold on.
Okay, perfect. Make sure I look good.
This way. This is for the YouTube clip. Gotcha.
Okay, thank you.
Over to you.
All right, so thank you very much. It's very nice to be here. I'm from the United States. I live near the Boston area, and I've been coming to England for quite a while. As John mentioned, I met him. I was doing a PhD at the University of Pennsylvania, and my advisor sent me over to the Cavendish lab where I met John. He was originally an experimental... Okay, technical problem solved. Just that's what we do, right? So, as I mentioned, John was an experimental physicist working on shock and things like that. I turned him on to polymers and mechanical engineering, and I think that's my greatest accomplishment for English academia, is getting John interested in being a mechanical engineer and working on polymers. I'm going to talk about, what the talk today is about is my background. I wanted to explain to you what I've done in my career. It's been about 30 years now. And basically I'm going to tell you about this latest company that I have founded. It's called Ionic Materials. And we're working on a very significant energy problem. As everybody knows, energy is a big topic these days, and the people that can come up with the technology to help our energy solution is going to be very valuable. And I'm going to talk about the challenge for batteries, what specific problems we're working on and what our solution is. I'm going to explain to you how we're going to solve this problem with our technology. And at the end, I think this is an inspirational lecture. I just want to tell you about some things I've learned along the way. As I mentioned, I worked for a large company for half of my career. I've been actually a professor at Tufts University overlapping all this time. In the second half of my career, I've set up actually 3 companies. And being an entrepreneur can be very challenging and very rewarding. So I have a final few thoughts on what I've learned throughout my years of being an entrepreneur. So again, I've been working for about 30 years. When I got my PhD, I was deciding, should I go into academia or should I go into industry? I ended up looking at both. I had opportunities in both. I ended up going to Bell Laboratories because I really wanted to be in a place where it was a world leader in innovation. And at Bell Labs, I worked on some fundamental technologies that went into product development. One of those was developing overmolded semiconductors in order to make things like smartphones. Another thing I worked on was the world's first fiber to the home system. So the reason we have internet right now in very fast speeds because of that work from Bell Laboratories. I somehow got the entrepreneurial itch, and I started a company called Quantum Leap Packaging, and it had to do with a new polymer for semiconductor packaging. And I quit my job and started the company myself, and I learned a lot. I always say I have an MBA from the School of Hard Knocks because I learned how to raise money, to build a company, create ideas, hire people, get them excited. We eventually sold that company to another company, and we spun off a company And the third thing I did was I had an idea about batteries. I thought that batteries were a real material science problem, and people were working on anodes and cathodes. And I thought the real problem was with a liquid electrolyte. And I came up with an idea to make a polymer electrolyte to help solve that problem. That's what I'm going to talk about today. And as I mentioned, I've been at Tufts University since 1990. I'm what's called a professor of the practice. I teach part-time from an industrial perspective, and I have a limited number of students that I guide on PhDs, and if things work out, they come work at the company afterwards. I have a student right now who's starting, and I'm going to be collaborating with John, and you'll see her over here at Imperial College. So why are batteries so important is because there's a significant problem with energy and storage, and we're trying to basically go away from carbon-based fuels, and we want to go to storing energy with batteries. Lithium-ion batteries have been the energy storage technology. They started in about 1990. They were invented in Japan. We actually just recently had 3 Nobel Prize winners for the original invention of the lithium-ion battery. And essentially what's happened is they've hit their, they basically hit a wall as far as performance. We're trying to make bigger batteries that work in cars, and because of the fact that we have a liquid electrolyte, there's just not a lot of safety measures around them. Also, we're trying to develop batteries to be low cost that can store energy so we can enable more things in the grid. And the lithium-ion batteries have basically hit their limit as far as performance and cost. So there's many battery solutions. And what my company has been doing is we have an idea to create a new material. It's the world's first polymer electrolyte that conducts ions at room temperature. And we believe it's going to enable a next generation of batteries that will help with these problems. So to characterize the problem, who's familiar with the petawatt hour? Anybody? So you may not know this, but there's a lot of energy consumed. There's 100 petawatt hours of energy consumed in the world. That is a lot of energy. 91% of that energy comes from carbon-based fuels, 91%. 1/3 of it is due to oil for cars, transportation, and 2/3 has to do with fuels for the grid, things like natural gas and coal and things like that. So the goal of the world, as everybody knows, is to try to eliminate that, because all of these carbon-based fuels leads to war, human rights abuses, pollution, and basically economic inequality. It's a big effort and war between countries based upon these types of fuels. One of the reasons why companies like mine are working on it is because it's an extremely large market. Batteries can be a huge market. Right now, they're $80 billion, and it's going to go to $200 billion very quickly. And to put it into perspective, other markets of that magnitude are things like beer, advertising. So there's a lot. The message behind this is it's a big market and there's a lot of room for innovation. This is an area for engineers and scientists to get involved with for innovation. It's a huge opportunity. And here's a quote I love. It's from actually the oil minister in Saudi Arabia. The Stone Age did not end for lack of stone, and the oil age will end long before the world runs out of oil. And that's what we're trying to do, is to end the oil age. Okay, and so these are the areas that we're working on. We're trying to, you've probably seen a few electric vehicles in England. There's a few Teslas here. I know there's a Renaults here. But we want to be able to make batteries that enable electric vehicles, and the way to do them is to be able to make them for the right cost. We also want to make batteries to enable things like solar and wind. The problem with solar and wind is the fact that it's intermittent to store energy. And right now, batteries are not cost-effective or safe enough to make big battery plants to store that energy. And those are the problems my company is working on. That's our vision. Our vision is to take this material science we've developed and help try to solve this issue. So my company was started, this one was started in 2012. It's based upon developing a new polymer electrolyte material to replace a liquid electrolyte material such that it conducts lithium ions, it's inherently safe, and then it allows for higher energy density anodes and cathodes. And the result of all that is making lower cost batteries. So what we can do is, the previous slide was enabling electric vehicles and enabling grid storage. So what I've shown here is we've got a lot of academic collaborators that we work with, including Professor Deere at Imperial College. And we have, interestingly enough, I've raised a lot of money for this company. It's pretty close to $100 million. And it's been interesting trying to raise money. We've initially raised money from financial institutions. I actually have 5 billionaires that I've gotten to know that have invested. And we have several strategic companies, some of them are listed, some are not, that we're working with and collaborating to take our material, turn it into a battery, and to provide solutions like I showed in the previous graph. So I'll mention we're trying to do something called the solid-state battery. There's been 3 approaches of solid-state batteries up till now. One is a glass sulfide solution, which is pioneered by some companies and people in Japan. And its flaw is the fact that it is very sensitive to moisture and gives off a very toxic gas if it's exposed to moisture, and there's manufacturing issues associated with it. Another material is oxide ceramics, and it has some interesting properties, but scaling it up into high volume manufacturing is an issue. So polymers, I believe, are a very high ability to manufacture in high volume. If you can extrude and injection mold, there are processes available to manufacture in high volume. There was never a polymer that could meet all of the requirements for batteries. There was one polymer that was actually developed many years ago it's called polyethylene oxide, that does conduct ions, but it actually works on something called, where most engineers here, you're above the glass transition temperature and the chains transport the ions between the chains. But you have to heat the battery, and another problem with it is it doesn't work at appropriate voltages. So my company has basically developed this polymer that basically is a solid state material that we replace the liquid electrolyte with a solid. So the way a conventional battery is built is you have an anode and a cathode, and you soak it with liquid electrolyte. So we now have been working on a polymer where we replace the liquid electrolyte completely and put in our solid polymer. We have 3 layers of a solid state battery, basically. And the advantage of that, as I'll show, is that you can basically make this battery inherently safe, and you can manufacture it with high volume plastics manufacturing capability. This is one slide on the mechanism. The previous polymers I mentioned was something called polyethylene oxide, and it worked on a concept above its glass transition temperature called chain mobility. We've developed a new mechanism where it does not, the transfer of ions do not count on the chains moving, and this allows for ionic transport in a wide temperature range and a very high ionic conductivity level. So that is the intrinsic invention of my company that is enabling this new polymer, which can enable new batteries. And as I mentioned, what's interesting about our material is the fact that it can be manufactured with standard lithium-ion battery equipment, does not need to have new manufacturing equipment invented to make the battery. We are much better than the prior polymer because it only worked at high temperatures, and some of the other materials like sulfides are challenged in the fact that you have to develop new manufacturing capability for it. So that's what we believe is our advantage in this technology. Getting back to polymers, it's my view that polymers have been a technology that's enabled lots of new products. Like one material that came about 70 years ago was PVC. PVC enabled a new generation of materials for homes. PET was developed to be a blow-molded material to replace glass bottles. Some of your grandparents may remember, when you used to get milk from the milkman, it was in a glass bottle. You would drink it, give it back, they'd clean it and send it back to you. But the advent of new polymers has made product development much better, and these are huge potential new businesses if you can come up with the idea for a new polymer that enables new functionality. And we think our ionic materials polymer will be in that category of new inventions. Okay, so what are the challenges? As I mentioned, there's three things with lithium-ion batteries. There's safety. The liquid electrolyte in current lithium-ion batteries that you have in your smartphone, it's like kerosene. The material is very flammable, and what can happen is if the anode and cathode, for any reason, short, heat can be generated and the flammable liquid electrolyte can explode. And that's been the fundamental problem. People are trying to make higher energy density batteries, but making the anode and cathode closer together. That's what happened with Samsung a couple years ago, where they got too close and exploded. We're trying to make bigger batteries to put in electric cars. We're trying to make big, huge batteries for grid storage, but the problem is they're very unsafe. So they are limited on energy density because of that reason also. You can't pack so much energy into a battery without there being a safety hazard. And the third issue is cost. We're trying to make electric vehicles cost effective, and one of the reasons why they're not is because you have to put so much safety equipment around the battery, and it's just very expensive. So you've probably heard in the news all sorts of explosions, like this was a laptop. In the center is a bunch of electronic cigarettes that somebody tested and blew up. So I don't know if anybody here vapes, but besides the vaping issue, they actually have lithium-ion batteries. And then, there was seats of airplanes that exploded from battery chargers. So I mentioned Samsung had a problem a few years ago with, it cost them over $5 billion to come back from that safety issue. And I just had someone call me, I don't know if you heard about this, but there was a boat full of scuba divers in Santa Barbara, California in September, charging their batteries inside the boat, and those batteries caught on fire, and 34 of the people on the boat actually died as a result of that. It was a very serious accident. I had a very long and interesting talk with the owner of the boat. And then recently, too, in the United States, there's been a lot of Tesla fires, and these can be very dangerous. People have died already, and one of our government agencies basically has put out an alert, the fact that defects have caused an alarming number of car fires, and there's going to be some investigation into that. Okay, so now I want to show a little bit more about the details of these types of safety issues and talk about our solution. My company was featured on a show in the United States called NOVA, the Search for the Super Battery. And I have a couple of segments on this.
Lithium-ion battery cell uncontrollably overheats. It's called thermal runaway. Leanne and Josh break it down for me. A plunger crushed the inner cell of the battery until a negative and positive electrode made contact, a short circuit. Just like when dendrites short out a battery, electrons flooded across in a massive discharge, creating heat, which then turns some of the liquid electrolyte into gas. That burst open the battery's foil pouch, and then the vaporized electrolyte ignited. That's known as venting with flame. All the fire and heat set off reactions in other nearby cells, sending them into thermal runaway as well. In the end, the fire reached a temperature of over 1,800 degrees Fahrenheit, easily hot enough to melt the aluminum used in the battery.
Yeah, so you can see it's a considerable problem, and again, we're trying more lithium-ion batteries that are larger and larger and have significant energy density. And this is the fundamental problem from safety point of view. There's other problems. One of them, as I mentioned, is cost. And right now, the cathodes in the latest generation of batteries have a significant amount of cobalt in them. And cobalt is a very expensive element, and it's also mined in a couple of Congo, where there's a lot of social issues with child labor and things like that. So we're trying to eliminate the amount of cobalt in cathodes, and when you lower the cobalt content, the actual cathode gets to be more unsafe. So liquid electrolytes, it's even more dangerous when you minimize the cobalt content. So one of the things we're trying to do is to have our polymer replace that electrolyte to minimize that cobalt to make batteries less expensive. And there's the concept of range anxiety. If you're driving an electric car, you have a certain amount of capacity, and we want these batteries to have anodes and cathodes that have a lot of energy such that, you know, we have decent range in our cars, basically. Okay, so again, our solution is to provide this polymer electrolyte that replaces the liquid, and the idea is to give the battery inherent safety, much lower cost, and to enable things on the upper right is, and I'll show you a demo of this, is lithium metal, which has 2x the energy density of graphite, which is the typical anode in a lithium-ion battery. And so our solution, you know, we want it to be inherently safe, and there's many interesting features of that. By making it inherently safe, you want to, when you go on airplanes, you know about the fact that you can't bring certain lithium-ion batteries and you can't check them. So we want to make a battery that actually is inherently safe to fly. We want to make the polymer so it can enable higher energy density anodes and cathodes like lithium metal. So instead of having a 100 or 200 mile range on your car, we want a 1,000-mile range on your car. And basically, we also want the material to be compatible with next generation anodes and cathodes, which are much cheaper, like lower cobalt and no cobalt cathodes. Okay, so I think we have another clip here. Get this place. This shows our solution now.
Here's another demo using an iPad with its original battery removed, and in its place, one of the mics that's even bigger than the last one cut to pieces. And I'm going to stick a screwdriver through it, like you saw in those YouTube
Don't do
videos.
this at home.
Here we go. So far, I'm not seeing any fireball. Okay, you've done it. You've made a battery that doesn't explode when pierced. At the very least, I expect to see some smoke. I expect to feel some heat. There's nothing.
Yeah, it's because of the solid plastic electrolyte. It's not flammable, and it's very insulative. It doesn't get too hot, and it doesn't burn.
And it keeps working.
That was unintended consequences.
Hey, do it again. My worries is too high, and the tax rates are insane. And I dented my finger. Alright, now it's not going to turn on now. Oh, come on! Come on!
We're a good team. I was a straight man, and he was a, yeah, but he was, he's actually, this was on a show called The Search for the Super Battery. And this was right after the Samsung fires, and they were explaining what was going on with batteries, and they kind of found us by accident, and they came to our lab, and he did that with no rehearsals. We just gave him a battery, and it was pretty amazing, actually. I think I have one more video which explains, I think he's
Compared to a
explaining,
typical
yeah.
lithium-ion battery, Mike replaced the liquid electrolyte and the separator with his special plastic to create a completely solid battery. Unlike the liquid electrolyte, which easily catches fire, Mike's plastic is flame retardant. And even though it's solid, amazingly, it allows lithium ions to pass through it at a rate equal to or better than the current liquid electrolytes. And here's the best part. The plastic physically prevents dendrites from shorting. That means that Mike can go back to a lithium metal negative electrode, potentially doubling his battery's energy density.
Yeah. So anyway, so this again shows, you know, where our key technologies were material scientists developing this new material, and starting this company is we're trying to develop a product that is significant and can help solve this energy problem. And right now, we're at the stage of the company is we've proven a lot technically. Now we're in the stage of actually scaling up this technology. Oh yeah, and here's another one we like too. This is the ballistics test. People tell me when I'm in foreign countries, this is a very American test because we're shooting at the battery. I did this in Japan once, but yeah, it just demonstrates. So we did this actually for the military, and it just demonstrates the safety aspect of our polymer. So we did this actually at DuPont in the United States. They test their Kevlar vests, and they actually did this with a high-speed camera, actually. And What's interesting is after we shot it, it actually still worked. You know, that was an unintended consequence, but it still worked. So that's an American test. We don't do that in England. So maybe John will do it.
I like that.
So where we are is Solidstate has been the holy grail. With decades of research, people still say they're not going to be available to 2030. And sometimes they say startups work faster than big companies. So I've been in Europe a little bit visiting with some car companies, and our plans is to introduce the first solid-state battery to an automobile in 2023 in mass production. And we're actually giving these, not us, but our cell suppliers are giving batteries with our material to begin what they call A-sample testing next year. And we're working with the US companies in the military to try to develop some products for 2021 that are safe. And we're working with one US company that is the largest US renewable energy company. And we're planning on producing cells for them to start testing in big volume in 2022 for renewable energy. So, you know, again, the way I look at my company is we're trying to develop this material that creates this battery that solves these significant energy problems, and this is where we are in our journey to trying to do that. Okay, so I thought I would just also, since this was an inspirational talk, to throw in a few slides about, you know, what I've learned about being an entrepreneur, and I also want to recommend it to you. I started out just like you. I was an engineer. I got a bachelor's, a master's, and then a PhD. And then, as I said, I took my first job in a large company, and then I got the entrepreneurial bug, and I started to do this. So anyways, I threw a few slides in here of what I've learned and what I'm proud of as far as being an entrepreneur. And this now is my third company. So the way you start a company and to get people excited, I know I started my 3 companies by myself, but the way I did it was to create a vision. This is what I want to do. This is the vision and mission of the company. And you know, I said to myself, just very simple, we have this energy problem. As I said earlier, 91% of the energy is carbon-based fuels. And we have and batteries are the solution, but we have all sizes. We have many people working on different types of battery solutions. And my vision was to come up with this polymer electrolyte that was different than anyone that was created before. And the goal was to invent it, develop it, come up with a business model, cost model, and then apply it to that problem. And that's the first thing you do as an entrepreneur, is to come up with that vision as to what you want to do and to try to have it make sense. Along the way, I met some interesting people. My partner is a guy named Bill Joy up there. He's actually the inventor of Unix, and he's the inventor of Java. He was the founder of Sun Microsystems, and he was actually the original investor in my company. And along the way, I've met people like Bill Gates. That's Katie Coleman. She's an astronaut. She actually has a PhD from Polymer Science from UMass. That's Jeff Williams. He's actually the COO of Apple. That's Mark Doyle. He's the CEO of DuPont, and that's the leadership of Samsung. So along the way, what's been great is meeting people like this that are interested in solving that problem, that have been giving me help throughout the years. Some lessons learned, and you know, entrepreneurship isn't for the faint of heart, because it's not easy, but you have to have a passion for it. And as I found, you know, you get much higher highs and much lower lows. You always have to have the positive attitude. And I call it making lemonade out of lemons. It is hard to go on vacation initially. My bosses are people that give me money, so it's a little bit different than a boss in a company, but I report to financial people, and that's quite different. Things will go wrong, and you have to be definitely determined, and you have to be careful about spending money. We build a lot of demos to show things work, like you've seen some of those demos. And when I raise money, I always raise it at a point where I've proven something new. And I've been able to, a lot of venture investors like to invest in internet-type companies, but I found a way to find people that will invest in material science-type companies. What I'm proud of is creating something from nothing. I think some people remember, like my wife, that I started the company in my basement. What's been really satisfying is creating interesting jobs for people throughout the years. I think I've created over 150 jobs. And I've seen people in the United States, universities are much more expensive than here. And I've had several people working for me send their kids through college, including me. I've actually sent 2 daughters through college, and it's very expensive. Small companies move fast. Large companies are hindered by bureaucracy. And like I was with a very large car company in France earlier this week, and we talked about the fact that their vice presidents told me from an R&D point of view, they're a dinosaur. They like working for us because we help them move fast. Some things I've learned about leadership is that it's all about setting an example and being optimistic. So the leader of the company, if you're going to start a company, has to set a vision that everybody will agree with and wants to come into the company every day and work hard. And I set stretch goals and set a tone of confidence. Things will go wrong, but we always need to keep people's spirits up, and we always celebrate success. And in my job, the thing I like about the company I work with, I got like 60 people now, and it's the best place I ever worked. People every day wake up, they want to come to the company because of our mission and the type of environment we have. And that's what you can create in a company, is to create that culture. So what I'm proud of too, investors call me a serial entrepreneur, I like that. They want to create something for nothing. So the entities are enduring. And now through creation, I've learned how to raise money, building a team, motivating people, developing boards, and creating partnerships. So that's it.